This is a stochastic process, Model 6 Martingales, Lecture 2, definition and simple examples. In the last lecture, we have covered conditional expectation, expectation of x given y and its properties, filtration f of t, t over the time, t over the 0 to infinity and its properties. Then conditional expectation of random variable x of t given that the filtration f of s and its properties. In this model, we will discuss an important property of stochastic process, Martingale. The Martingale referred to a class of betting strategies popular in 18th century. The concept of Martingale in probability theory was introduced by Paul Levy, and much of the original development of the theory was done by Joseph Doob. Part of the motivation for that work was to show the impossibility of successful betting strategies. The definition of Martingale is as follows. Let omega f p be a probability space. Let t be a fixed positive number. Let the collection of filtration f of t, where t over from 0 to capital T, be a sub sigma fields of f. So the f is the sigma field and the filtrations are the sub sigma fields of the f. And the probability space is defined in omega f and t is a fixed positive number. Using that, we got a filtration of sub sigma fields in the range 0 to capital T. If the expectation of x of t exists for fixed t, x of t is a random variable. So if the expectation of x of t exists, or in other words, in the random variable is integrable. Also, if x of t is ft measurable, this also we discussed in the last lecture. Whenever we say the random variable is ft measurable, that means that the sigma field generated by the random variable x of t, that should be contained in f of t. If this property is satisfied by the random variable for a given filtration f of t, then we say for a given sigma field, we say x of t is ft measurable. So the second condition is x of t is ft measurable. The third condition, not only for a fixed t the expectation exists and the random variable is ft measurable, the conditional expectation, that is the expectation of x of t given the sigma field f of s, is same as the random variable x of s. The s can take the value from 0 to small t, where t can take the value from s to capital T. If these three properties are satisfied by a collection of random variables, that is stochastic process xt, then we say the stochastic process has Martingale property. So in this definition, we started with the probability space and we fix some positive integer, positive number. Using that, we create a filtration, and those filtrations are nothing but sub sigma fields of f. F is a sigma field. If you have a collection of random variables, that's a stochastic process. For fixed t, it is a random variable. So that random variable satisfies the integrable property and ft measurable property, and the conditional expectation over the sub sigma field f of s, that is nothing but the filtration. That is same as the random variable x of s. In that property is satisfied for all s and t lies between the interval 0 less than or equal to s less than t less than or equal to capital T, then we say the collection of random variable x of t or the stochastic process x of t as the Martingale property. So here this stochastic process satisfies the Martingale property in the interval 0 to capital T, because we are checking the conditional expectation in the interval 0 to capital T. Therefore, this stochastic process has a Martingale property in the interval 0 to capital T, not 0 to infinity. If that is satisfied by for all t, then we can say that random variable or that stochastic process x of t, or this stochastic process x of t has a Martingale property in the range 0 to infinity. Now, we present the definition of Martingale in discrete time. A sequence of random variables, that is xn, n varies from 1, 2 and so on, of random variables has a Martingale property with respect to the filtration fn, where n is also running from, where n also takes the value from 1, 2 and so on. If for fixed n, the random variable is integrable, that is expectation exists, and also each random variable xn is fn measurable. The third condition, the conditional expectation of xn plus 1 given the filtration f of n is same as xn for every n. Then we say the random variable has the, then we say the stochastic process has the Martingale property, or the collection of random variable or the stochastic process has the Martingale property. So this is the definition corresponding to the discrete time. The previous definition is for continuous time. Equivalent definition of Martingale is as follows. A real valued adapted process x of t, where t is lies between 0 to capital T, to the filtration f of t, where t is lies between 0 to capital T, with the expectation is finite, expectation exists, is a Martingale. For instance, n of t minus lambda t for t greater than or equal to 0 with the intensity lambda with respect to the natural filtration f of t, t greater than or equal to 0 is a Martingale. Here n of t is a Poisson process. Some remarks are as follows. The Martingale property is equivalent to the conditional expectation of xn minus xm given the filtration f of m is equal to 0 for every m less than n. So the Martingale property is same as the conditional expectation with the difference of the random variable, expressing that the increments xn minus xm given the past fm as expected value 0. The Martingale is a stochastic process that on the average given the past does not grow or decrease. That is the meaning of the above expression. A Martingale is a stochastic process that on the average given the past does not grow or decrease. If it increase or if it decrease, we have a different name for that particular property. Now we are discussing it does not grow or decrease. So that is called that stochastic process is called Martingale. A Martingale has a constant mean. That means if you have a stochastic process satisfying the three conditions, hence the stochastic process has a Martingale property or the stochastic process is a Martingale, then the expectation is going to be constant. That is, expectation of xn is same as expectation of x naught for all n. Note that Markov property can also be given in terms of expectations. In other words, the expectation of xn is same as expectation of xn for all n, that is same as a martingale is thus a stochastic process being on average station. Average stationary means it has the time invariant property in average or in mean. Usually the stationarity property or the time invariant property is discussed in the distribution, but here in the martingale it has a expectation of xn is equal to expectation of x naught for all n. Therefore, a martingale is thus a stochastic process being on average station. These above remarks is also valid for continuous time. While martingale concepts involves expectation, the Markov process concepts involves distribution. Whenever you discuss a stochastic process with the martingale property, it involves the conditional expectation. Whereas whenever you discuss the stochastic process with the Markov property, it involves the distribution, conditional distribution. A Markov process need not necessarily be a martingale, because the stochastic process having a Markov property, therefore it is going to be a Markov process. A stochastic process having a martingale property, martingale concepts involves the conditional expectation, whereas the Markov property concept involves the distribution. Hence, a Markov process need not necessarily be a martingale. The martingale has a lot of applications in branching processes and finance. Now we are going to consider the few examples. Example 1. Let x1, x2 be a sequence of independent random variables with the expectation of xn is equal to 0 for all n. We are not giving the distribution of the random variables. We have said it is a sequence of random variable and all the random variables are mutually independent. And you know the expectation of the random variable is equal to 0 for all n. Now you are defining a new random variable. S naught is equal to 0 and Sn is equal to sum of first n random variables x size for all n is equal to 1, 2 and so on. The filtration Fn is defined from the sigma field generated by the n random variables x1 to xn with the sigma algebra generated by the first n xi's. Now we are trying to compute what is the conditional expectation of Sn plus 1 given the filtration f of n. That is same as conditional expectation of, you can replace Sn plus 1 by Sn plus xn plus 1 because that is the way we defined Sn. Sn plus 1 is going to be first n plus 1 random variables. The first n random variables will be Sn. The last term will be x of n plus 1. The way we created the the way we created the filtration Fn is nothing but the sigma field is generated by the first n random variables. Therefore, the Sn random variable is the Fn measure. Because each xi's are Fn measurable. Each xn is Fn measurable. The Sn is nothing but the first n random variable xi's random variable summation. Therefore, Sn is also Fn measurable. Xn plus 1 is independent of Fn because Fn is the information till first n xi random variables. Therefore, xn plus 1 is independent of fn. Therefore, a conditional expectation of Asn plus 1 given the filtration Fn, the information up to n, that is nothing but, since Sn is Fn measurable, therefore Sn is known, because you know the information till n, that means Sn is also known. Therefore, Sn has to be treated as a constant. So the conditional expectation of Sn given Fn is going to be Sn. The second term, the conditional expectation of xn plus 1 given Fn. Since Fn is independent of xn plus 1, it is not, the information up to n, it is not going to affect the value of xn plus 1 or the random variable xn plus 1. Therefore, it is just instead of conditional expectation, it is a expectation of x of n plus 1. But already we have made a expectation of n is equal to 0. Therefore, the expectation of n plus 1, it is all for all n expectation of n is equal to 0. Therefore, expectation of n plus x of n plus 1, this is also 0. Therefore, the conditional expectation is going to be Sn. Since you know the information up to n, the Sn is a value. So the conditional expectation of Sn plus 1 given Fn is equal to Sn. This is nothing but the Martingale property, the last condition of Martingale property in a discrete time. Whenever you want to conclude the given stochastic process is a Martingale, has a Martingale property, three conditions has to be checked. The first one is expectation exists. You can find out the expectation of Sn. Since expectation of xn is 0, expectation of Sn is also 0. The second condition, the Sn has to be a Fn measurable. That is also verified. The third condition, the conditional expectation has to be Sn. This is also verified. So since three conditions of the definition which we discussed for the discrete time satisfied, we conclude the given stochastic process Sn, the collection of or the sequence of random variables Sn, has a Martingale property. This Martingale property is with respect to the filtration Fn, because this Martingale property is with respect to this filtration. There may be a possibility this stochastic process may not have the Martingale property with respect to some other filtration. So the given stochastic process Sn has a Martingale property with respect to this filtration Fn. The second example, this stochastic process is a continuous time discrete state stochastic process. So here let n of t, where t varies from 0 to infinity, be a Poisson process with the intensity lambda or parameter lambda, and the f of t is its natural filtration. The natural filtration means it has the information till time t, and each random variable n of t for fixed t is ft measurable. That is the meaning of natural filtration. We know that for fixed t, n of t is a Poisson distributed random variable with the parameter lambda. Therefore, the mean of n of t, that is same as the parameter lambda. So the first condition is satisfied. The second condition, for fixed t, n of t has to be ft measurable. Since it is a natural filtration, the n of t is a ft measurable. The third condition we are going to verify. The conditional expectation of n of t given f of s, where f of s is the filtration at time s or the information till s. Obviously here S is less than T. So to find out this conditional expectation, what we do, we add and subtract n of S with the n of T. So instead of a conditional expectation of n of T given f of S, we subtract n of S and add n of S. Expectation is a linear operator. Therefore, you can split these three terms into two different expectations, conditional expectation. Therefore, the first one you can keep n of T minus n of S. The second one you can keep it separately n of S. Hence, you have conditional expectation of n of T minus n of S given the filtration f of S plus conditional expectation of n of S given f of S. The first term, this conditional expectation is nothing but you know the information till time S, and we are asking the conditional expectation of n of T minus n of S given f of S. That means this T minus S and S, this is a non-overlapping intervals. S is a point, T minus S is the non-overlapping intervals. So this is the random variable corresponding to the non-overlapping interval with respect to S. Therefore, you know the property of Poisson process. For S less than T, n of T minus n of S is nothing but the increments. The increments are stationary and independent. Therefore, the n of T minus n of S is independent of f of S. If it is independent, the conditional expectation is nothing but expectation of n of T minus n of S. You know the Poisson process properties. Since n of T is a Poisson process, n of T minus n of S for fixed T and S, this is a Poisson distributed random variable with the mean lambda times T minus S. Therefore, this conditional expectation will be lambda times T minus S based on the n of T minus n of S is independent of f of S, and for fixed S and T, n of T minus n of S is a Poisson distributed random variable with the mean lambda times T minus S. Whereas the second term, conditional expectation of n of S given f of S, that means for information till time S, what is the expectation of n of S at the same time S. So since you know the information till or up to the time S, n of S is constant. N of S is a constant. Therefore, expectation of constant is a constant. Therefore, it is n of S. It's not a lambda times S, because the you know the information till time S. Once you know the information till time S, that means you know the value of n of S also. Once you know the value of n of S, therefore n of S is no more a random variable. So it's a constant. So expectation of a constant is a constant, so it is n of S. Hence, conditional expectation of n of T given f of S is same as, you can take a lambda T in this side. So conditional expectation of n of T minus lambda T given f of S is same as n of S minus lambda times S. If you see, this is a expectation of n of T minus lambda S given f of S, that is same expression. Therefore, as such, expectation of n of T given f of S is not n of S. It has the some positive value. T minus S is always greater than 0. Therefore, lambda times T minus S will be greater than 0. Therefore, this conditional expectation is always greater than or equal to n of S. Hence, n of T is not a martingale, whereas if you treat n of t minus lambda t as a stochastic process over the t ranges from 0 to infinity, then this stochastic process is a Martingale. The n of t is not satisfying is same as n of s. The conditional expectation is not equal to n of s, but it is greater than or equal to n of s. Therefore, n of t is not a Martingale, whereas if you make another stochastic process, that is nothing but n of t minus lambda times t, or t greater than or equal to 0, then this stochastic process satisfies the third condition and also satisfies the other two conditions. Therefore, the n of t minus lambda t is a Martingale. Third example, this is related to the application of finance. Consider the binomial tree model. Let Sn be a stochastic process and Fn be its natural filtration. Define the probability of Sn plus 1 given u times Sn given Fn, that is same as that is P, and the probability of Sn plus 1 is equal to d times Sn given Fn is equal to 1 minus P, where u and d are the next value of Sn with the probability P and Q respectively. Therefore, suppose the previous the nth value was Sn, then the next value will be, it is decremented with d, therefore d times Sn, or it would have been incremented with u, therefore u times Sn will be the Sn plus 1th value. Therefore, this stochastic process is called the binomial tree model. Now I am considering the discounted stochastic process, that is nothing but e power minus r times, basically e power rt s of t. Since it is a discrete time stochastic process, the first s1 is multiplied by e power minus r, whereas the second random variable s2 is multiplied by e power minus 2 times r and so on. Therefore, the nth random variable Sn will be e power minus n times r, where here r is the riskless interest rate. So, whenever you multiply the e power minus r times t, the corresponding stochastic process is called the discounted stochastic process. The discounted stochastic process is a Martingale if only if the right hand side is equal to e power minus n times r times s, because here it is a conditional expectation of e power minus n plus 1 times or Sn plus 1 given Fn. If this quantity is same as e power minus n times r multiplied by Sn, then this discounted stochastic process will be a Martingale, or it has the Martingale property. So this is the case only if the p value takes e power r times minus d and divided by u minus d. If the p is the probability of incremented by u, if the p is equal to e power r minus d divided by u minus d, then the discounted stochastic process is a Martingale. So that is possible because since p lies between 0 to 1, since whenever the r is the riskless interest rate, e power r is also lies between d to u. Therefore, the u minus d and e power r minus d, this values is going to be lies between 0 to 1. So therefore, with the proper value of r, d and u, the p can be, if the p is of this form, then the discounted stochastic process is a Martingale. Now we are moving into the fourth example. In the fourth example, we started with the filtration. Fn is a sequence of sigma fields, and this is the filtration. Let x be any random variable with the random variable is integrable. Define xn is a conditional expectation of x given f. So you are defining a sequence of random variables with the help of the conditional expectation of the random variable with a given the information up to n, or the filtration n. So suppose you want to prove this sequence of random variable or the stochastic process is a martingale, then it has to satisfy the three conditions which we discuss in the discrete time of a martingale property. So the first we are checking whether the random variable xn is integrable. So if you want to prove the xn is integrable, then you have to prove the expectation in absolute random variable has to be a finite. If that is finite, then the random variable is integrable. So this is same as expectation of in absolute. You can replace xn by expectation of x given fn. You can take the absolute inside the expectation, and this is nothing but it is a absolute of x, because that is a way we define, since xn be any random variable with the expectation is a finite, and you know the definition of expectation x given y is going to be expectation of x. So we are using that property. Hence expectation of x given the filtration fn is same as expectation of that random variable. So here the random variable is absolute x, and this is already proved that it is a finite, therefore this is also going to be finite value. Hence the expectation of absolute xn is finite, the random variable xn is integrable. So the first condition is verified. By the definition of conditional expectation, xn is a fn measurable. The way we have written xn is a expectation of x given fn. So this is the definition of conditional expectation. Whenever you write conditional expectation of x given fn and that exists with the xn, that means the random variable xn's are fn measurable for all n. So by the definition of conditional expectation, xn is fn measurable for all n. So the second condition also satisfied. Now we are going to verify the third condition. The expectation of xn plus 1 given fn is same as, you can replace xn plus 1 by the definition, that is expectation of xn given fn plus 1. You are replacing xn plus 1 with the conditional expectation given fn. You know the property of the filtration. The filtration property is f1 contained in f2, f2 is contained in f3, and so on. Therefore fn is contained in fn plus 1. If you have two sigma fields and one is a sub sigma field of other one, fn is a sub sigma field, fn is a sub sigma fields of fn plus 1, then the conditional expectation of conditional expectation x given fn plus 1 given fn is same as conditional expectation of x given fn. We are using the conditional expectation given sigma fields with two sigma fields fn contained in fn plus 1. We are using the property. Hence expectation of x given fn, by the definition expectation of x given fn is nothing but xn. Therefore this is equal to xn. So left hand side we started with the expectation of xn plus 1 given fn. The right hand side we will end up xn. This is the third property of this is the third condition we have defined it in the Martingale property in discrete time. So hence all the three conditions are satisfied by the sequence of random variable xn's. Therefore, the stochastic process xn is a Martingale with respect to the filtration f. Because we have used this filtration to conclude xn is a fn measurable and find out the conditional expectation is same as xn, and the random variable xn is integrable. Hence, the stochastic process is a Martingale with respect to the filtration fn. Now we present the example which was introduced in the beginning of lecture in this model. So this is the example we have given as a motivation for the model Martingale. A player plays against an infinitely rich adversary. He stands to gain ₹1 with the probability P and lose ₹1 with the probability Q. We are defining the random variable xn, the player's cumulative gain in the first n games. What will be his fortune on the average on the next game, given that his current fortune? We are asking the measure in a conditional expectation. The game is fair if and only if this sequence of random variable xn is a Martingale. And that is possible. This sequence of random variables or this stochastic process will be a Martingale when P and Q is equal to off. That means when the game is fair, that means whether he will gain ₹1 or he lose ₹1 with the equal probability 1/2 and 1/2, then in the game is fair. Whenever the game is fair, the given stochastic process is a Martingale, and also whenever the given stochastic process is a Martingale, in that case the game will be a fair game, and that means the P and Q will be off 1/2. The conclusion is, it says that the player's expected fortune after one more game played with the knowledge of entire past and present is exactly equal to his current fortune. The conditional expectation of his one more game expected fortune given the knowledge of entire past and present, that means the filtration till time t or till time n in the discrete case, that is same as exactly equal to its current fortune. That means it is same as expected, that is same as x suffix n for a discrete case, or it is x of t for a continuous case. So whenever the game is fair, that is a P and Q is equal to off, then the given stochastic process xn is a Martingale. And the conclusion of this problem is the player's expected fortune after one more game played with the knowledge of entire past and present is exactly is important, because later we are going to say more than or less than. For that we are going to name the different. So here it is exactly equal to his current fortune. Now we are moving into the concept called Doob's Martingale process. When we say the given stochastic process is going to be a Doob's Martingale process or Doob's process. See the definition. Let yn be an arbitrary sequence of random variables, and suppose x is a random variable with expectation in absolute finite, define xn is the conditional expectation of xn given y0, y1 and so on till yn for every xn where n is running from 0, 1, 2 and so on. Expectation of x given fn plus 1 given fn. We know that fn is contained in fn plus 1, and using the property this becomes expectation of x given fn, that is same as x suffix n. In essence, as n increases, xn approximates x and the approximation becomes more refined because more information has been gathered and included in the conditioning. Thus, xn, n is equal to 0, 1 and so on forms a martingale with respect to y suffix n, where yn is equal to 0, yn for n is equal to 0, 1, 2, called the Doob's process. Now we define submartingale and supermartingale. Submartingale and supermartingale by replacing the equality in the equation 1, the equation 1 in the definition of martingale, whether it is a discrete time or the continuous time. If you replace the equality sign with a greater than or equal to or less than or equal to respectively for any 0 less than or equal to s, less than t, less than or equal to capital T, the third condition, the first two conditions are expectation exists and then xt is ft measurable or xn is fn measurable. That's the two conditions. So there is no change in those two conditions, only the change in the third condition, that is by replacing the inequality in equation 1 of with the greater than or equal to, less than or equal to, then the corresponding stochastic process will be call it as submartingale whenever it is greater than or equal to sign, or it is supermartingale if a conditional expectation is less than or equal to x of s. If it is equal to for all this interval, in that case it is a martingale. If this property is satisfied greater than or equal to s, where s is less than t and t is less than or equal to capital T, then the stochastic process is called a submartingale, and the less than or equal to condition is satisfied, then the stochastic process is called a submartingale. Now we present the Poisson process is a submartingale. We take the same example, n of t is a Poisson process with the intensity lambda, and earlier we have proved n of t is not a martingale because a conditional expectation is greater than or equal to n of s, because t minus s is greater than 0, lambda is strictly greater than 0, therefore this quantity is greater than or equal to n of s. Hence, conditional expectation of n of t given f of s is greater than or equal to n of s, it's always greater than or equal to for all s less than t, where t is less than or equal to infinity. So this condition is satisfied for all s and t, hence the given stochastic process, that is the Poisson process, is a submartingale because of this greater than or equal to sign. Now we present the Wt square is a submartingale where Wt is a Brownian motion. Wt is a Brownian motion, so we are going to use the property of Brownian motion, that is a one particular important stochastic process which has a lot of applications in financial mathematics. So here we are going to prove Wt whole square is a submartingale. How? The conditional expectation of a Wt whole square given f of s is you add one term and subtract one term, that is plus ws minus ws inside the Wt whole square. Using the identity, Wt minus ws plus ws whole square will be same as Wt minus ws whole square plus 2 times ws Wt minus ws plus ws whole square. So why I am doing this way of adjustment? Because I am going to use the property of non-overlapping intervals or independent. We are directly checking the conditional expectation. The first two conditions are obviously satisfied. The first one is Wt is integrable. The Brownian motion, for fixed t, Wt is normally distributed with the mean 0 and the variance t for a standard Brownian motion. Therefore, the mean exists. The second one, Wt is ft measurable. So whenever we didn't discuss the filtration, that means we have a natural filtration f of t. Whenever we have a natural filtration, that means this random variable is ft measurable. F of w of t is ft measurable. Therefore, second condition is also satisfied, and we are checking the third condition. The third condition, the right hand side, Wt minus ws whole square plus 2 times ws times ws minus ws plus so on. So now we are applying the conditional expectation here given f of s. Therefore, the conditional expectation is a linear operator. Therefore, it is a conditional expectation of this term given f of s, conditional expectation of this term given f of s plus conditional expectation of this term given f of s. You know that f of s is nothing but the information up to time s, and Wt minus ws, that is also normally distributed with the mean 0 and the variance t minus s. I am discussing about the standard normal distribution. Later we are going to discuss the Brownian motion in detail. So here I am going to use only the distribution and the mean of a Brownian motion as well as a independent property. So here the Wt minus ws is independent of f of s. Therefore, the conditional expectation is nothing but expectation of the Wt minus ws whole square. Since Wt minus ws is normally distributed with the mean 0 and the variance t minus s, this this expectation is nothing but the t minus s. The second term, again 2 times conditional expectation of ws multiplied by Wt minus ws given f of s, and the f of s is independent of Wt minus ws, and you have the information till s. Therefore, ws has to be treated as a constant. So the 2 times ws will be treated as a constant. So hence expectation of Wt minus ws given f of s is nothing but expectation of Wt minus ws, because of f of s is independent of Wt minus ws, and you know that expectation of Wt minus ws is 0, because this is normally distributed with the mean 0, variance t minus s. The third term, the conditional expectation of ws whole square divided by f of s is nothing but ws whole square, because you know the information till time s. Therefore, ws whole square has to be treated as a constant. Expectation of constant is constant. Hence, expectation of Wt whole square given f of s is nothing but t minus s plus 0. So hence t minus s plus ws whole square. So this is obviously greater than or equal to ws whole square. Therefore, the Wt whole square is a submartingale. because it satisfies the third condition with the greater than or equal to sign in the conditional expectation. Therefore, the stochastic process Wt whole square is a submartingale. Some remarks. A stochastic process, let's say of random variable xn, is a submartingale with respect to the filtration Fn. N varies from 1, 2 and so on, if and only if minus Xn is a supermartingale with respect to the same filtration F. The if and only if is very important. Whenever you have a submartingale, you can always convert it into the supermartingale with the minus sign. Or if you have a supermartingale, you have a stochastic process with the supermartingale property satisfied, then you can convert this stochastic process into the submartingale stochastic process by changing the sign. Note that both the stochastic process, we are discussing the martingale property, submartingale or supermartingale property with respect to the same filtration. That is important. You cannot convert submartingale into supermartingale with a different filtration. Not in general. If you have a same filtration, then you can transform the submartingale into supermartingale by changing the sign in both ways. The second remark, a stochastic process Xn, n varies from 1, 2 and so on, is a martingale with respect to the filtration Fn if and only if and only if Xn is both submartingale and the supermartingale with respect to the same filtration. That means if you have a given stochastic process of martingale, if and only if the same random variable will be treated as a submartingale as well as supermartingale, because we are replacing the equality sign by greater than or equal to. Similarly, less than or equal to. We are not replacing by strictly greater than or strictly less than. Since we have replacing the equality sign in the conditional expectation of the third condition in the definition of martingale with less than or equal to, greater than or equal to. Hence, if you have a martingale, then the same thing will be supermartingale as well as submartingale. Similarly, if you have a stochastic process is both submartingale and supermartingale without changing the sign or without doing any change, the same stochastic process is a submartingale as well as a supermartingale, then definitely that will be a martingale. Because if it is both submartingale and supermartingale, that means there is no the conditional expectation with greater than or equal to or less than or equal to. It must be equal to the conditional expectation. Hence, the given stochastic process is a martingale. These above remarks is also valid for continuous time. In this lecture, we have covered the definition of martingale in continuous time, the definition of martingale in the discrete time. Then we have discussed a few examples, and followed by that we have discussed when we can say the given stochastic process is a supermartingale or submartingale. We have given few examples for the supermartingale as well as submartingale also. And finally, we have given some remarks over martingales, submartingale and supermartingales. Here is the list of references. With this, the lecture 2 of Module 6 is completed.